In this video, we're going to look at an application of linear functions, which is linear inequalities. And basically, this is what happens when you take out the equal sign in a linear equation and replace it with any of the four inequality symbols. These look very similar to linear equations. Again, the only difference is that we have an inequality symbol in the middle instead of an equal sign. When we start to graph them, in the beginning, the process is the same, but then we have a couple extra things we have to look at the end. So to start, I'm going to treat this like y equals negative 2x plus 1. I have my y-intercept of 1. I have a slope of negative 2, so we come down to the right 1, and then up 2, and back 1. But now I'm not going to connect the dots right away. This is where I have to start to look at that inequality symbol. Here we have or equal to, which if you remember from before, would have told us that we needed to use a solid or closed circle when graphing. That's because any number that worked for that inequality, if they were equal on both sides, would be included in the solution set. So that was our or equal to. If we had the open circle, that was from strictly less than or strictly greater than. So that would be like the inequality on the right here. And points where they were equal on both sides would not work for the inequality. When we graph on the coordinate plane, this is going to tell us what type of line to use. So if we have the or equal to, it means the points along that boundary line are included in our solution set, because if we look at the point 0, 1, 0 is less than or equal to negative 2 times 0 plus 1, that point would work. Whereas if we didn't have that or equal to, we wouldn't be able to include those points in our solution set. Because we want to include those points in our solution set, oh, that's wrong. This is going to be 1 on that side. I was going to say, that doesn't look quite right. 1 is less than or equal to 1, which works. Because we do want to include those points in our solution set, we're going to use a solid line when graphing. If we had something like the right-hand side here where it was strictly greater than, we would use a dotted line to show that that's where our boundary is, but we're not including those points in our solution set. So I'm going to go ahead and draw that solid boundary line on my graph. Do the best job we can here on the tablet. But now we need to remember that when we talk about inequality, it's not just that one value or that one set of values that works. You'll see that my boundary line divides my graph into two regions here. I need to figure out which of those two regions contains the points where the y-coordinate is less than or equal to negative 2 times the x-coordinate plus 1. In order to do this, I'm going to pick a point anywhere in the coordinate plane that's not on the red line to test. Usually we're going to test the origin. And if we look at our graph, we see that the origin is in what I've labeled to be region 1. This means that if I plug in 0, 0 to my inequality and I get a true statement, all the other points in the same region as the origin are also solutions, and we would shade that part of the graph to show that we want to include them. If it turns out that I plug in the origin and I get a false statement, that means that the origin and all the points on this side are not part of my solution set, and that my solutions sit on the other side of the graph. So we substitute in the origin, we say 0 is less than or equal to negative 2 times 0 plus 1, and we get 0 is less than or equal to 1, which is a true statement. So we're just going to go ahead and shade in that side of the boundary line. And now we have a complete graph of this inequality. Go ahead, pause the video, and see if you can at least get the boundary line down for the second inequality. Alright, so we've got a y-intercept of negative 3 and a slope of 2/3, so we come up 2 over 3. And if we look at our inequality, like I was talking about before, this is strictly greater than, which means that the point along this boundary line don't actually work for this inequality. So if we try our y-intercept, we would have negative 3 is greater than 2/3 times 0 minus 3. Now I would say that negative 3 is greater than negative 3, which isn't true. So that's why we have the dotted line here to show that we're not actually including those points. Now we want to pick a point to test, and again the origin is not on our line, so we can test that one out. And we have 0 is greater than 2/3 times 0 minus 3, or 0 is greater than negative 3, which is true. So again, we're going to shade the side of the graph that includes the origin. Your shading doesn't have to be pretty, but you just want to make sure it's very clear which side is shaded and that you don't completely cover up or go over your boundary line so that we can't see what it is. So the first thing we're going to do, just like when we started graphing systems of linear equations, With linear inequalities, we're going to start by graphing each inequality. So for this first one, we started out with two simple inequalities that are both in slope-intercept form. So I'm going to do my first inequality here in red. My y-intercept is -3. My slope is 1. So I can get all my points plotted here. And if I look at that inequality symbol, it's strictly greater than. So this is going to be a dotted line. And because it's greater than, we're going to shade above the line. Another way we can check is check any point that's not on the boundary, so we could use the origin. We would say 0 is greater than 0 minus 3, that's true. So we're going to shade above our boundary line here. Alright, now we're going to graph our second line. We'll do that one in blue. So we have y is less than or equal to -5x plus 3. So we come to our y-intercept, we have a slope of -5. We've just got 2 points. And this is less than or equal to, so that's going to be a solid line. Whoa, that's way off. So we'll come, still off. Try it one more time. A little curvy, but gets the job done. And so we've got that, and since it's less than, we're going to shade below the line. So we're going to come down and shade all of this. Alright, so now if we look at our graph, we have 4 different regions. We have region A here, region B here, region C, and region D. If we're talking about points that work for both inequalities, we want points that sit in the overlap of the 2 shaded regions. That overlap is going to be here in version B, where we see both the red and the blue overlapping. So my final answer is going to be this shaded area here, and I'll do this in purple, and that is going to represent my solution set. All the points here shaded in purple are solutions to both inequalities. So just like before we were looking for a point that worked for both equations, here we're looking for the set of points that work for both inequalities. And we're going to shade that in. So my shaded region in purple is my solution set. We're looking for that overlap. Go ahead, pause the video, see if you can find the solution set to the second system here. Alright, so if we look at this system, we've got our first line in red. We have y-intercept of 2, down 1 over 3 for our slope. That was greater than, so we have a dotted line and we're shading above. And then for our second line, we have y is greater than or equal to 2/3 x minus 1. So we rise 2, run 3, have a y-intercept of -1, solid line. And again, not in purple, we're going to shade above. We look for the overlap, which is all our stuff in purple up here, bounded by those 2 lines. We can also work backwards. So we can take a look at each inequality, find our slope and y-intercept, think about which way we're shading, and then see if we can't figure out the system. So if I look at this first one, I have a y-intercept of 2 and a slope of -1. So that is going to be, we'll write it down here, y, we have -x plus 2. It's a solid line and we're shading above, so it's y is greater than or equal to. Then here we have a y-intercept of -3, and our slope, we rise 2, run 3, so our slope is 2/3. So we have y, 2/3 x minus 3, strictly going to be greater than or less than because it's dotted and we shaded above, so strictly greater than. So our system here would be these 2 inequalities. If you were asked for them in standard form, you could transform each inequality into standard form. Go ahead and pause the video, see if you can identify the next system. Alright, so if you look at our top line, we have a slope of -1, a y-intercept of 1, and we're shading down with a dotted line, so that's y is less than -x plus 1. For the bottom line, we have a slope of -1 again, y-intercept of -3, dotted line, and we're shading up, so it's y is greater than -x minus 3. Alright, now for this question, similar to the ones we did when we just had one linear inequality. We're given the inequality, and we're given a couple of points that we want to figure out whether or not they are solutions. So there are two ways you can do it. The first being you could just plug the coordinates in for x and y into each inequality and see if you get true statements. If you do for both inequalities, it's a solution. Or you can graph the system and see if the point lies in that shaded region. So go ahead and pause the video and see if you can identify which of these 6 points are solutions to the system. Alright, so if we go ahead and look at these points, we have -1, 4, which sits on our solid line, but also would be shaded by the blue line if it was not on that borderline, so that is a solution. -5, 2 is clearly in our shaded region. 0, -2 does not work because it sits on that dotted line, so that is not a solution. 0, -1 just slides into our shaded region, so it's good. -1, -1 again is clearly inside, and then if we look at the point 2, 1, it sits on the solid line, but that wouldn't be shaded by the blue line, so it's not a solution.